Hello students, welcome back. We went through a bunch of antiderivative problems and let's go to the next set, improper integrals. Determine whether the given integral converges or diverges. Now, have you seen this integral before? You have. It's right here. Of course, this was antiderivative, the indefinite integral. This one is definite. Let's go back to this problem here. What did he do? Well, there's a solution. It's a power function because the denominator is nothing but a complete square. So this is the antiderivative you get. So in this problem, oh, never mind. Let's start from here. So negative of 1 over x minus 2. And then x is going from 4 to infinity. So what do you get? Negative 1 over infinity minus 2. Infinity minus 2 is infinity, so we still have 1 over infinity type. And that's going to become 0. And then 1 over 4 minus 2, right? Negative, another minus, so plus. So this is 0 plus 1/2. So the answer is 1/2. And if I ask Mathematica to do the computation, copy and paste and run it, yes, 1/2. Oh, by the way, previously I mistyped and then got 0 here. And then, will that give me something? No, it turns out nothing. And the reason is because, let's see, if you do from 0 to infinity, it crosses the vertical asymptote at x equals to 2. Do you see this? Or, let's see. x squared minus 4x plus 4. Okay, about that. Okay, here's a graph. And then if you take the integral from 4 to infinity, then 4 is over here and this part. That really small part, that's something we are considering. Or even if you start from, say, 3 to infinity, how about this part? That's okay. But if you start from 0 to infinity, the infinity part doesn't really contribute too much. X equal to 2 part, this part blows up to infinity. X equal to 2, that's bad. And we have divergence there because of x equals 2, not because of infinity. So if I start from x equal to 2, that's going to be a problem, but anything greater than 2, that's going to be okay. But of course, there's no reason to go down that much, so let's start from anything reasonable. I decided to start from 4 or maybe 3. As a matter of fact, the topic about vertical asymptote is topic for the next problem, so maybe I shouldn't have taken that much time explaining that. Let's talk about the next problem there. This problem is really about vertical asymptote, you see. X squared minus 4x plus 3 plotted from x equal to 0 to 5, what do you get? We have this vertical asymptote here, that vertical asymptote here. If you take the integral, how about the shaded part around this vertical asymptote? Will that blow up to infinity? That's the problem here. We don't have the upper end or lower end going to infinity or negative infinity. It's the vertical asymptote that's causing a problem. And by the way, have you seen this before? You have? It's right here. And what was the integral? decomposed by partial fraction, and then what do we have? We have two logarithms. And do you recall the behavior of log functions? Log of 0 that go to infinity, log infinity that 2 go to infinity. So we have bad behavior both ways. Indeed, we have something like this. So we can decompose the denominator, we can factor the denominator like this. And then we can decompose the integral from 0 to 1 because we have first vertical asymptote, and 1 to 3, and then 3 to 5, the second vertical asymptote. If all three integrals are convergent, you'll have a plus b plus c. That's going to be the value of this integral. It'll turn out, however, all three are divergent. If any one of them is divergent, then all bad. But in this case, all three are divergent, and the reason is the same, log of 0. So if you just go from 0 to 5 to the antiderivative function, looks like nothing is happening, but we're having bad behavior because of the vertical asymptotes. By the way, what am I talking about? Let's see. What did I just talk about? This one. Okay. Okay, so that, and because of all that, and then that's going to, let's see, 0 to 5. All right. So this is gonna be and then plug in x equals to 5. So 5 minus 3, so we have log of 2. And then 5 minus 1, we have log of 4. And then plug in 0. 0 minus 3, but absolute value log of 3. And then plug in 0. And if you do it like that, you get an illusion that you have finite value. Log of 2 minus log of 4 minus log of 3, and then that's going to be 0. So it looks like you may have something, but this is an illusion as a matter of fact. We have log of 0 popping up in the middle after decomposing like these due to the denominators, due to the vertical asymptote, and then we have three integrals and all three are divergent, so it's divergent. This computation here is not a correct computation. Okay, next. How about this problem? Have you seen this before? And yes, you have. It's this problem. It's arctangent problem. And okay, let's calculate this. The antiderivative is arctangent of x minus 2, as you've seen before. And plug in infinity minus 2, so it's just infinity. And plug in 1 there, 1 minus 2, so the arctangent of negative 1. And then arctangent of infinity is pi over 2 because, you know, tangent of pi over 2 in negative direction and as in increasing direction goes to positive infinity. Or, oh, maybe it's better this way. Yeah, maybe it's this easier this way. If you plot out tangent function, you have horizontal asymptote forming here and there. This is pi over 2 and that's negative pi over 2. Yeah, it's easier this way. So arctangent of infinity, that's pi over 2, arctangent of negative 1, and use this triangle, Pythagorean triangle, and the arctangent is 1. That means the vertical over horizontal is 1, so we have to have isosceles triangle. So it's 45 degrees. And then because this is -1, we need negative pi over 4. So eventually we end up with 3 pi over 4. You can actually calculate it. But of course, you don't really have to calculate. You can simply use the, what do you call, you can use, what do you call, the comparison test, excuse me, yes, comparison test. And this integrand is asymptotically equivalent to 1 over x squared because that's the highest order term. And this one is convergent, so that too is convergent as well. You can answer like that, by the way. Excuse me, is the integral going from 1 or going from 2? Let's change it from 1. Okay. I can make it starting from 2, but that's not really interesting because the arctangent of 2 minus 2 is 0. So arctangent of 0 is 0. So this part is arctangent is 0. So that part just becomes 0. So the computation is not as interesting. So let's keep it this way. All right. We went through improper integrals. It turned out that this one and that one can be done explicitly. And this one divergent.